Yeah. Okay, so good morning all. So this is our sixth day of our Parikshala. So in the first 4 days, we have seen the quantum chemistry, theory, Monte Carlo. The remaining is we have this today is molecular dynamics. So it gives me great pleasure to introduce Dr. Debashish Kundu, who is from the Institute of Chemical Technology, ICT, Panakoda campus, Jalna. So he did his PhD at his IT Guwahati in 2019, and then he did his postdoc at the Department of Materials Engineering, IISc Bangalore. His key research areas are thermodynamics, then molecular dynamics simulation, oil and gas, and hydrogens. So overall, he has around 30 publications till date, and he has also 3 sponsored projects running. So with this, I will again extend a warm welcome to Dr. Kundu, and I invite you to please start the session.
Thank you, sir. Thank you, sir, for the kind introduction. So, am I audible? Okay. So, good morning to all. So, today we will start. We will divide our session into some sections. So, in the first half, we will go through the molecular dynamics theory, and in the second half, we will show you how to do the molecular dynamics simulation using GROMACS. Okay. So, basic theory. Okay. So now brief introduction. I'm not asking your introduction, but I'm giving my introduction. So myself, Dr. Debashish Kundu. I'm an assistant professor in chemical engineering from ICT Marathwada campus, Jalna. This is basically the second campus of ICT Mumbai. You can see here, this is Mumbai. Everyone knows. And from the Mumbai, around 450 kilometers east or 500 kilometers east, there is a place called Jalna near Aurangabad, where the second campus of ICT is. So I belong to this place. I mean, okay, my workplace, and it is probably the equal distance from Hyderabad as well as from Mumbai. Right. So you can take a flight to Hyderabad as well as you can take a flight in Mumbai and reach to Jalna to know more about MD simulation. Okay. Okay. So with this brief introduction, we start. Okay. What is MD simulation? So far as from the introduction of SAR, I have learned that you have gone through like the QC quantum chemical calculation, right? DFT, density functional theory, and then you have done MC, Monte Carlo, right? So have you understood all of them? Quantum chemical calculations, like by doing it into the Gaussian, etc. And then MC, for MC, what software you use? TAUI. Okay, TAUI, right? Okay, that's good. So, okay, that is a third type of simulation process that we generally do is the MD, molecular dynamic simulation. So as the name suggests, it is basically deal with the dynamics of molecule. It deals with the dynamics of molecules. Molecules are made of atoms, so it essentially also deals with the dynamics of atoms as well. Right? The difference with MC is MC basically in the Monte Carlo code, they do not take the atomic properties. We basically assume some beats or something. Based on that, we derive the potentials and then we do the calculation. Earlier case, where at the, let's say in the 60s, 70s or 80s, the computational power were not that huge. So what used to do, people used to take some, assume some beat. Okay. I mean molecules, they assume the connection of beat and then they generate the potential and eventually calculate the molecular properties or the thermodynamic properties or the transport properties, right? So at that is basically called the quartz grain simulation. Okay, so quartz grain molecular dynamic simulation, which is essentially very much same with respect to the Monte Carlo. You do not take the atomic properties, you do not take the atomic orientation or the molecular orientation, you just assume some sort of collection of a bead, derive your potential and do the calculation. Now with the advent of the computational power, people have rejected that idea and generally they come to the proper atomistic structure. Okay. And then the concept has begun that all atom molecular dynamic simulation, and over the time, people rejected that all atom term and only come through the term molecular dynamic simulation. Right? Okay. Okay. So next is as the definition says, I just read the definition. So molecular dynamic simulation is a computer simulation method for computing the equilibrium and transport properties of a classical many-body system. So what we assume that in the molecular dynamics, see, there is an important term called the classical. So classical, when we say that the classical, what it gives? The classical mechanics, right? So can anyone answer that? What is the basis of classical mechanics? Laws of motion, right? So Newton's second law of motion is the basis of the molecular dynamics. So when we solve the Newton's second law of motion, like force equal to mass times acceleration for a many particle system, and do the subsequent integration, because force equal to F is mass times acceleration, that becomes the F equal to M, okay, d2x dt2, right? Right. So this is the Newton's second law of motion, right? So the molecular dynamics simulation is essentially based on the classical mechanics, which is the basis is the d2x dt2, right? Now, molecular dynamics simulation has some limitation. The basis of this classical mechanics says its limitation. Okay, how many of you are purely the computational chemist or computational physicist? How many are experimental and how many are mixed? Just raise your hand. Pure computational chemist or pure computational physicist? How many? Pure. Experimentalist? And mix? Okay, good. So basically, experimentalist has some reservation. When they see that the MD guy or MD girl, they are just presenting something, they say that, oh, you can do this, you can do this, you can do this. Basically, they think that everything we can do with the MD. But there is a certain limitation that you need to understand. And on the first day, whenever someone is pitching you to do something, you should tell that what we can do, what we cannot do. The idea lies here, the classical term, second law of motion. As you know that Newton's second law of motion, that does not tell about the bond breaking phenomena. That means the quantum chemical phenomena, submolecular phenomena, like the bond breaking, bond formation, right? Those cannot be explained by the molecular dynamics simulation. Clear? So that's the first limitation. Whenever we have to go to that bond breaking or bond formation phenomena, although some newer mixed algorithms are there, but still their validity is debatable. So to do that, those kind of things, bond breaking or bond formation things, we need to go to the DFT part. Okay, like the ab initio DFT Okay, ab initio MD, etc., or like periodic DFT. I'm sure that you have learned the periodic DFT, right? So those kind of things. So basically, the sub-molecular phenomena like bond breaking, bond formation, reaction, molecular dynamics cannot do that. If some experimental faculty or some experimental collaborator comes to you and say that we are doing the catalyst reaction, could you check the catalyst reactivity or something with the MD? No. We cannot see the reaction part, but we can see the interaction part. That means the molecular dynamics, whatever the case we are doing the molecular dynamics, is only we are seeing the non-bonded interactions. Okay, where it can interact, that we can only see. And that is huge. That is huge because when Newton created this F equal to ma, he didn't think that after 400 years, someone will come and discover the drug based on this formula, right? Because when the molecular dynamics started, basically it started with the to check the interaction of the drug molecule with different let's say protein or etc. Right? So only thing the non-bonded interactions are being studied. That whether that drug is particularly can affect that non protein or let's say different type of body fluids. There the molecular dynamics. I mean, from there the molecular dynamics has started. And for that, there is a specific type of file type has been created, which is called the protein data bank file that we will see in our subsequent lectures. So clear what we can do with the molecular dynamics? We can check the non-bonded interactions, and that is huge. If you closely analyze any sort of interactions in your system, let's say you are doing the extraction. Let's say you want to study the drug interaction with particular fluid. You can see that in all those cases, the non-bonded interactions are playing the major role, not the bonded interactions. Okay, so therefore, the molecular dynamics play a role. Even nowadays, okay, there is a very hot topic that the lithium ion transportation in the LIV. That also, that the transportation part, those things, it is very hot topic for the molecular dynamics simulation, right? Yeah. So the next point is, it is used to analyze the physical movements of atoms and molecules, providing a dynamic view of system evolution. So what we do generally in the molecular dynamics, we generally observe that how the molecules or atoms are moving in a system. The second limitation of the molecular dynamics is molecular dynamics will only give you the trajectory and energies. It is your duty to convert those trajectories into observable quantity. It is not molecular dynamics duty will convert the those trajectories into the into this observable part, right? Let's say till today we are facing challenges to accurately compute viscosity. Although viscosity is a transport property, thermal conductivity is a transport property, ionic conductivity is a transport property, but that is only applicable up to the mesoscale. When you go to the atomistic scale, this molecular dynamics can predict, but still the accurate formulation of the trajectories are still not well explored. So basically, this viscosity, ionic conductivity, thermal conductivity, they are still elusive concept. For some system, it works. The same formulation for the other system, it won't work. There are different strategies are available. People are now what do you call integrating the AI algorithms with the MD simulation. So to overcome that, but still these are on the very much research stage. So basically, we can predict the transport properties because the molecular dynamics give me the physical movement. That means the trajectories of the atoms as well as the molecules It's your duty to write the code and convert them into the transport property, right? So these are the two things. Okay. So in the molecular dynamics, some steps are available. So we can divide a molecular dynamics into 3 steps. I mean, I am saying with respect to the GROMACS concept, but in the NAMD or LAMS, it can be up to the 4 steps. Okay, let's assume that the 3 steps. First is the minimization. Or we can say the energy minimization. Then is the equilibration. And then is the production. Okay. So these are the basically 3 steps are being followed in any kind of molecular dynamics simulation. What are they? So energy minimization. Let's take an example. When you enter in this room, what did you do? Did you sit on the same chair? I mean, did 2 persons sit on the same chair? No. Everybody maintain a proper distance, right? Everybody maintains a proper distance so that everyone can sit. When we create the structures in the molecular dynamics framework, they are not like energetically minimize position. They are like randomly oriented. So what we do, we create one program that is called energy minimization, which will minimize that energy. That means that will place all the atoms in a energy minimized space, right? After that, when you enter and sit on the room, is it possible to start writing or following my lecture within a second? No. It takes at least 1 minute or 2 minute time to accommodate with respect to this environment, right? Then you will be able to listen my lecture. In the molecular dynamics, we call this is equilibration. That means adjusting to the environment. Whenever the energy is minimized at the same time, it cannot give the output. Same like your behavior. After 1 minute or 2 minutes, you open your notebook or file and then start writing or start following my lecture. That means you are delivering something. You are basically producing something. In the molecular dynamics, we say this is the production stage. So basically, in any kind of molecular dynamics, we have 3 stages. That is the energy minimization, equilibration, as well as production. Now, in the second step, what I said that we analyze the physical movements of the atoms and molecules, providing the dynamic view of the system. So basically, whatever the trajectories we generally collect and analyze, that is with respect to the production stage. Okay? So therefore, if you read any kind of MD simulation paper, you will see that if the equilibration is done for 10 nanosecond, the production is done for the 50 nanosecond or something more than the equilibrium, right? Okay. So what is the next part? So this is property system no longer changes with the time, followed by the actual measurement. Okay. So the observable quantity is measured by expressing the observable quantity as a function of position and momentum of the particle of system. So basically what it says that we will collect the trajectories and it is our duty to convert those trajectories into physically measurable system. At the end of this session, probably around 1 PM, we will see that how to do it with the example of viscosity ionic conductivity, and diffusivity. Okay, so this is a brief history of MD simulation. So in the 1950s, it has been pioneered by Fermi, Elder, and Rehman. Then there is a concept called force field that I will discuss explicitly, and that has been developed in 1970s. After that, I mean, still this time, the molecular dynamics program used to run in the single core, single CPU core, right? After that, the parallel computing has been developed, and it has accelerated the output. Yeah, it has accelerated the output, and nowadays it has explicitly used. So you can see some important years like 1964, the first simulation of liquid argon. So whenever someone started any new thing, they used to start with respect to the ideal case. So liquid argon, that means argon is considered as the ideal fluid, and based on that, the first simulation come. Then liquid water at 1974. Then the protein behavior of protein is in 1977, and you probably have heard about this name. Okay, Martin Karplus. For the molecular dynamics, he won the Nobel Prize in 2014, 13 or 49. Just in those days. And now people are doing longer simulations. I mean, till what I can see that when I used to do the MTech, at that time, I see the papers of 2005, 6 or 2008. That time, an RDF plot, I mean the radial distribution function, that is the very basic plot of molecular dynamics, will give you a JPCB paper. Okay, today if you do the RDF and okay, try to submit it, probably you will end up some XYZ unknown open access or journals. So because the advent of the parallel computing as well as newer algorithms demand more from the researcher, that beyond the RDF, there is more things. Okay, we will see that how to compute them. Okay, some objectives I have already discussed, so I just go through that. Basically, this molecular dynamics that creates the structural and dynamic behavior of the many body system. So what are the many body systems? It started with the liquid argon, but now we can generate the complicated systems like the biomolecules, polymeric systems, interaction with surfaces like membranes. Although the creation of the membrane geometry is really tough, the porous electrodes, whether it has the regular defect or induced defect, that you can create and study. And with the advent of LIB, lithium-ion battery supercapacitor, the transport of ions have become a very huge field in the MD. Are there anyone working in the transport of ions? Okay. MD or DFT? Okay. Both. Okay. Okay. So as I said that MD simulations play a significant role in the drug discovery and the development process, helping to evaluate the binding energetics and kinetics of the ligand receptor interaction. See, one important thing is given, that binding energetics. When you insert a drug in silico manner, in silico means you are doing, I mean, there are three things: in vitro, in vivo, and third thing is in silico. In silico means whatever the drug, how the drug will behave, that you are studying in the computational phenomenon, right? Okay. So basically, what it does, whether the particular drug, or the API, active pharmaceutical ingredient, that will affect or that will interact with a particular protein, that has been determined with respect to the binding energy. We do the MD simulation, we check that by giving the motion, to the particular API or the drug molecule, whether that API is very close enough with the targeted site. If it happens, till it has not interacted, it will come very close to the targeted site. And based on the closeness, we determine the binding energy. And that is sufficient. That is sufficient to conclude that this is an useful API or active pharmaceutical ingredient for this particular disease. Okay. It is not like that will break the bond and do something else. No, that is not the MD job. For that, you have to go for the other type of, let's say DFT. Okay. But again, in the DFT also, to simulate a protein as well as, do these things require huge amount of computational resource, huge amount. Okay. So that is basically the ligand receptor interactions. That means by calculate the binding energies, how close they are. In the API, let's say it's a API, which part of the API is towards that protein. Those kind of things are basically derived from the MD simulation. So be very clear, huh? I have seen, even I have faced, because I am not a very old faculty. I just started my faculty career, 4 years back. Okay, I frequently encountered this thing from the experimentalist, or when my students give the presentation, experimentalist used to ask these things. You can do this bond breaking. No, we cannot do. MD, the basic principle violates that. That you have to say with this particular particular clarity. But you can go up to a certain part. For that, you need to identify the particular descriptor that you can predict with the MD. And that descriptor must be a non-bonded one. Okay. So if you closely, okay, let's say I'm giving one small example that presently we are working. I was discussing with the sir also that the browning of apple, cut apple. So we want to predict, is it recorded, right? Only audio to off the sector. Audio to off the speak. Okay. So the thing is, browning of apple. How to prevent the browning of apple? That we are trying to explain with respect to MD. Now, browning of apple. How to do that? When someone gives you the salad, let's say fruit salad, Zomato or Swiggy is giving you. See that some of the apples are I got browning. So what we do that we try to find out the descriptor first. Overall, for an experimentalist, it looks very different, but for an MD guy, it will be something different. So what we try? See that. So let's say I have a fruit salad box. Box is made of paper, essentially cellulose. Now what is happening? In the apple, what I have? Apple. So to do the browning, there is a particular enzyme is responsible. So what I take? The enzyme. I'm not taking the apple, I'm taking the enzyme. Right? And then the box will be covered with the plastic sheet. Right? So that plastic sheet I put it. Now the enzyme will get brown. How? If it comes into the contact of oxygen. So what I do in the MD simulation box, here I put O2 and N2. And I try to check the diffusion. Let's say this diffusion takes 30 nanoseconds. Usual, okay, usual packaging. But our case, we develop a new kind of membrane. Maybe the experimentalist gave the membrane that we have derived like this XYZ membrane. Okay, check that whether it will be important. I mean, whether it will be effective or not. Same thing, we put that membrane. So this membrane is commercially available. And this membrane is okay, lab generated. And then here we put enzyme. Here we put the enzyme. And same thing, we put the O2 and N2. Now here we see that the diffusion takes 30 nanoseconds. But here if it is 60 nanoseconds, then we can say that our membrane is not allowing the oxygen to get inside up to 60 nanoseconds. That means it is more resistive. So essentially, when I say the problem statement that we are working on the browning of apple, or let's say banana, etc., it becomes very unfamiliar to you. But then you have to find the particular descriptor for why it is happening. And then you try to write the code and do the simulation, you will get the answer. Very simple thing. Here, what we are doing, okay, what is the transport property? We are only checking. It is a diffusion. Non-bonded, it's not bonded. So we can check with the MD. So the idea is you have to identify the certain limitations and you have to identify that what physical descriptor you can define, and based on that you have to do the simulation. Right? Okay. Okay. So next is to study the properties of the material, such as crystalline, amorphous drug polymer formulation, drug-loaded nanoparticles, complementing experimental studies, etc. Then these things, okay, solubility, stability, these also we can study. If you closely go through the basic mathematical formulation of these things, you will see that none of them are bonded, all are non-bonded. Similarly, one problem came to me. Still I am searching that the physical. Okay, the problem is like came to me again with respect to the food, that the crunchiness of what do you call chips, the potato chips or the banana chips. But still we are searching what could be the physical descriptor of the crunchiness. Right? That we are still searching. If we can find it, we can get the solution. But for this browning, we have already found that what could be done. Then we are doing the simulation. So you have to identify the particular physical descriptor to get the MD simulation. Again, some repeating words to get the observing the important functional process like ligand binding, ligand voltage induced conformational changes. That is basically it can with respect to the biosystem or any kind of membrane transport or the lithium ion movement in the LIB. Okay, so there are some prerequisites of the MD simulation. Right. So when we do the MD simulation, now those days are gone when people used to open a line by line Fortran codes because earlier days people used to write in the Fortran. Now they have changed with the C++ and the modern algorithms are coming in the C++. But anyway, so but still we need some prerequisite thing to get the MD done. So first thing is initial coordinate and velocity of the particle. So if you open the book, good MD books, you will see that the line by line Fortran codes are written, right? Like Frankel, Smith, etc. But nowadays, softwares are there. We generally create with them, but it is good to have the idea of those look at Fortran codes, right? Then we require the interatomic potential functions as well as the parameters. We need some of the integration algorithms because, as I said, that this molecular dynamics is based on the Newton's second law of motion, and which is essentially a differential equation. Second order differential equation F equal to m times d2x dt2, right? That's a second order differential equation, right? So to get the x from d2x dt2, we need an integration algorithm. Next, we need the thermostat and barostat for ensemble. I hope that everyone knows ensemble, right? Ensemble. Everyone knows. Clear idea of ensemble? Can anyone answer what is the ensemble? One, give me one bookish answer and one practically relevant answer that everyone can understand. Come on. Okay, be a volunteer. You have done this DFT, you have done Monte Carlo. Machine learning is in much space, right? In 1970s, actually, the thing is, ensemble concept came first. For the statistical algorithm came at the same time. The classical came. That time is machine learning. No one knows. Okay. Essentially, some derivative with the partition function. Okay. So in the layman language, I mean, yes.
State of a system. The state of the system, so like entity, what are the parameters in one particular system? Basically, define the state of the particular system.
So what is state?
It's a way to define the probability.
Yes.
तो जब ब्रांड कराते हैं तो वो टाइम तो ऐसा जैसे एनबीटी है और एनबीटी है सपोज एनबीटी को लेते हैं तो उस रीजन को लेंगे जो करती उसको फॉलो करना एनबीटी को नंबर ऑफ मॉलिक्यूल प्रेशर और टेंपरेचर कांस्टेंट को फॉलो करेगा टाइम के साथ कुछ हम लोग नाइनो सेकंड 10 सेकंड के लिए मिनट होता है तो वो टाइम के साथ उस टाइम डिग्री को उसी रीजन को है जो इसमें एनटीटी को फॉलो कर रहा है तो जब उसका फिर एवरेज लेते हैं तो वो एक एग्जांपल
Average means statistical. Then, okay. So first thing is that first ensemble came, then this NBT came, right? Just I am giving you a layman example, okay? Because when I started to read the statistical thermodynamics, at the very first chapter, this ensemble concept is given. It is very hard to imagine what is the microstate, what is right? Okay. So let's consider that This is your simulation box. And you all are entities. Right? You all are particles. Now, how many of you probably, let's say 40, right? So 40. Now, at a particular instant, let's say 10, 44, 55 seconds. At a particular instant, you raise your hand. And all other is standstill. So when you raise your hand, that means your potential energy is changed because you have you have raised the hand against the gravity. So there is an energy change. What is the energy change? That is the Gibbs energy change, right? Gibbs energy change. So, but others are fixed. That is one answer, right? At the same instant, if you have stood up, others are fixed. That means your energy is also changed. That is another ensemble. So at particular instant, probably out of 40, 35 is doing something. So that means 35 different microstates are formed. When we go to the statistical thermodynamics, part, we look each and every microstate. When we go to the classical, then we say that okay, this is the state, this is the classroom. There is 40 number of students. So there are 40 number of students. But when we go to the microstate, I mean, when we go to the statistical, then we look what each of the 40 students are doing at a particular instant. Maybe at a particular instant, out of the 40 students, 35 is doing something, either scratching the head, raising the hand, or stood up, something, or writing something. So each of them will be a particular ensemble. That means only he or she is doing, others are remain constant or standstill. Now, when someone asks me what is the average energy change, then all the ensembles, that means all of your activity will be averaged together, and then you will get some answer. You will get the energy change. So sum of microstate energy change, the macroscopic energy change, right? Clear? So that is the layman concept of the ensemble. That means each and everyone will do something, others will remain standstill. That is the energy change. Now as we know that, again we come to the physical point. Okay, let's say a system gets, I mean the bookish idea, a system gets stabilized when its Gibbs energy minimizes, right? That we all know. But when I raise the hand or when I stood up from my sitting position, okay, how long you can raise your hand? Probably 2 seconds, 3 seconds. After that, you have to come down, right? Your hand to come down, right? Because that is not a energy minimum position. This is the energy minimum position. How long you can stand up? 1 hour. After that, you need a break. Okay, you need to sit down. So that's not the energy minimum position, but your sitting position is the energy minimum position, right? So after this, you will come to this position. So then there is an energy change. When I see the macroscopic view, the net energy change is 0. But from the microscopic view, there is an energy change of the raising your hand and putting your hand down. That is the ensemble average. So when you read this thermodynamics book like Sandler, use this concept, you will find that this microstate, all these concepts will be a little bit easier, right? Otherwise, starting with those concept is very difficult. So again, now I discussed the thermostat and barostat for ensembles. What you do in the experiment, when you perform an experiment, let's say doing a reaction. Who is the experimenter from? Yeah, you are doing some kinetics experiment. What it will create heat. What you will do? Let's say Okay, I just rephrase the question. The reaction will occur at 60 degrees Celsius and you are doing the heating. But generally, you don't have, you don't have the controller, so heat will tend to overshoot from the 60 degrees Celsius. So what is the mechanism we will use to bring the temperature at 60 degrees Celsius? Heat bath, right? That means you are putting an external jacket, right? Heat bath. You are doing that. That means whatever the temperature, it will shoot up. Ultimately, the heat bath will absorb and maintain the 60 degrees Celsius. Similarly, in the MD simulation, what we are giving? Okay, velocities. When we give the velocity to a system, what is the relation between the kinetic energy and the temperature? That is kT, right? So whenever we are giving the velocity, collision is bound to happen, temperature will rise. But simulation means exactly mimicking the experimental thing. Until unless you understand the experimental part, you cannot do the simulation. You can do the correlation, you can do the modeling, but you cannot do the simulation. Okay, so if I give the velocity to my system here, and let's say the temperature will rise, so my system will be unstable, right? Because it will shoot up, and the more the temperature rise, more the velocity will rise, right? So it has a reciprocal relation. We give the velocity, temperature rises. The temperature rises, again velocity rises. So there has to be some mechanism which will absorb this temperature. In experiment, what we do, if such kind of things happen, we put a jacket, right? We put the insulator. Same thing here, we will use the thermostat. That means that heat bath, this artificial heat bath we will give, so that it will absorb the additional temperature and bring our system into stability. Similarly, temperature, pressure, everyone knows the basic example is the pressure cooker. When the pressure cooker, when the sudden pressure rises, what happens? The pressure gets released, right? But if you do not, if you plug that outlet valve of the pressure cooker, what will happen after some time? Explode, right? So, but there should be some mechanism, some preventive mechanism where the pressure should be adjusted. Excess pressure should be adjusted. For the pressure cooker, what happens? The excess pressure is released to the atmosphere. In simulation, we don't have atmosphere. It's a computer code. So there we need to put some additional mechanism which will absorb the excess pressure. That's why we call the barostat. So the barostat, now the uses of the barostat and thermostat depends the type of ensemble we use. Clear? Okay. So when is the break time? 11:15. Okay, nice. Okay, so let's take about this initial coordinate. Okay, so initial coordinates and velocities. That is the first thing. So first, what we do, the positions of the particles are specified at the beginning of the simulation and often choose close to the local minimum on the energy surface. Again, the same thing. Let's say instead of this stairs, if you have a bench like where 3% of the student can see or 2 students can see, whenever you enter in that three student bench, can 5 students sit or 5 persons can sit? No, that will create the collision or that will create the instability. No one will be able to sit. No one will be able to sit properly. No one will be able to write properly. So you need a safe distance or a comfortable distance so that everyone can sit and everyone can concentrate. That is the same thing. that is in terms of the molecule and atoms. We say it the today chosen close to a local minimum on the energy, okay, energy surface. That means the atoms are properly oriented and their interactions in between them are minimum at the start. If at the start the atoms are very close, then energy will shoot up, and the thermostat and barostat, whatever I place at the initial part of the simulation, that will not be absorbed those additional energies. The simulation will fail. Okay, so initially we need to put our atoms or the molecules in a local minima. If you are working with the, let's say, the bead like argon, helium, which are the noble gas, you can place into a cubic lattice or face-centered lattice, etc. Okay, but if you are working, working with the polymeric systems, etc., there are specific ways how to put that I am discussing. Again, the particles should not have appreciable overlap or atomic or molecular core. Let's say you are working with the hexanes. Now, another hexane, it should be with some distance. It cannot be like in this way. Because then, at the very start of your simulation, when you give the velocity, these two hexanes, as they are basically overlapping, they will repel each other. Once they repel each other, so much energy will be created that your system will be failed. Because your simulation will be failed because the additional energies, the thermostat is not capable to absorb the additional energy. So you need to put some minimum allowable distance. Generally 2-3 angstroms are okay. So the random initial velocities are typically assigned to particles corresponding to a certain temperature as per the Maxwell-Boltzmann distribution. In earlier days, when people used to write the n number of Fortran lines, they used to do that. Now the softwares or the open source packages, they take care of this situation. The choice of initial velocities and coordinates affect the equilibration process. Poor choices can lead to the longer equilibration time, and it's a common practice to run multiple trial with the defined initial conditions to ensure the robustness of the result. Now again, we take an example of the experiment. When you do the experiment, you generally do a triplicated result, right? Right? Okay, let's say you are doing the distillation experiment. You get some result. Distillation, I am sure that everyone knows, right? Distillation. So you want to do some extraction or distillation. You do the triplicated result. That means you perform the experiment 3 times. Okay, so that, and then you take the average, and in your research paper you put the error bar to show that. The same thing we do here. Same thing. Here we do not generally. It's a general common practice that we do not take the output from a single simulation. Okay. We start our simulation, at least for any kind of things we do a triplicated. That means from 3 initial configurations. Okay, from 3 initial configurations, we start our simulation, get the result, that means the trajectory result, get the final observable data, average it, and do the error bar. Same thing we do. In your experimental thing, what you do? Let's say you are doing some distillation or extraction. You start with 3 fresh experiments right? 3 fresh experiment means 3 fresh initial set of data. In our simulation also, we start with the 3 fresh simulation initial configuration and do the simulation independently. And after that, whatever the results we get, we just average it and put the error bar. Same thing. So that's why it is saying that the choice of initial velocities or coordinates affect the equilibrium process. Equilibration process. Poor choice can lead the longer equilibration trials. And then it is common practice to run multiple trials. That is replicated, which is acceptable to the scientific community. Now, there is some example of this equilibration process. This basically happens when you do this post-scale simulation or like the molecules which has a very long chain or cross-link structure. Generally, I have seen that in my simulation. So that's a simulation box. Okay, and when I take a very long cross-link structure, what I find that the cross-link structure is generally go to the periphery and we get a hole here. So in my one set of experiment, I get this kind of data. But in reality, when I take the same polymeric structure and try to measure the viscosity, is it the same hole we observe in the reality? No, right? That means we need to take at least one configuration where this one will be eliminated. If we take this structure and similar to other configurations and do the equilibration and get my transport data, I will get very wrong result. Because that's not a physically realizable condition. So at that time, what I have to do, either I have to do the second set of equilibration at very high temperature or compress it very high pressure so that this is eliminated in one of my configuration. And then I do the production run, etc. Get my trajectory data, convert it into the transport properties, average it, I will get a little bit similar to my experiment. Clear? Right? So whatever the choice of initial velocity and the coordinate, that will affect the equilibrium process. Now, when assigning the initial velocity, a zero mean unit variance normal distribution is used to ensure the randomness and consistency. This is again, if you use the n number of Fortran codes, you have to do it. But nowadays, people generate with respect to the softwares. So this is essentially meaningless. Okay, now the modern approach to create the initial geometry. Okay, so again, the first things come is the QC. Okay, quantum chemical. So basically, unless until you do these two steps, this quantum chemical and the molecular mechanics, you cannot go for the MD calculation. That's why in this winter school, first 2 days were reserved for to understand the quantum chemical. If the molecular dynamics are given in the first 2 days, then probably these things will be very difficult to understand. So what happens basically in a very small molecule, we do the quantum chemical calculation, right? We optimize the geometry. What are the geometry optimization? Okay, what are the geometry optimization processes? You know? DFT, right? Density function theory. 34. Okay, molar per set. So any of this method, you create this quantum chemical calculation, and you get a optimized structure. Optimized structure. What is optimized structure? That means that has the minimum energy. right? That you get that. In some cases, it is very difficult to get the quantum critically optimized structure. Very difficult. Let's say I am doing a CMC simulation. That means carboxyl cellulose, which is having a 200 number of chains. It's very difficult. It's impossible. Okay. So at that time, what we will do? We will do the molecular mechanics calculation. That means molecular mechanics is very simple. For every unit, for most of the unit, some of the fragmented data, like what could be the bond, what could be the angle, what could be the diagram. You know, right? Diagram is what? Bond angle, right? No. Okay. So bond angle diagram, those are given. Those are given. Okay. When you draw, you draw your structure and run in the calculation, what it will do, it will see that, it will fragment your molecule. And whatever the properties are available in its library, that will add. Let's say if I take the hexane, so it has CH3 and CH2. It has CH3 and CH2. So now, if I want to do the calculation of the hexane, so what it will do? It will check its library. What are the properties of CH3 and what are the properties of CH2? Number of CH2 and number of, based on the number of CH2 and number of CH3, it will just plug and give you the optimized unit. So for very long chains of polymeric, we do that. In some cases, these two are that is the collection of structure from crystallographic files that is generally applicable for the which type of structure? Huh? Yes. This one. So which type of structure?
It's like. Okay.
Yes. Let's say you are working with a catalyst, inorganic catalyst, zeolite catalyst, MOA, COA, etc. Okay. Organic framework, organic framework. Those kind of cases, it is really difficult. Almost impossible to do the QC calculation because you can see that whatever the HA, DFT will apply after the optimization, the core will be broken.
Yeah.
Right? The core will be broken. There is a particular reason of the electron cloud. Those are the difficulties. So at that time, what people do, they rely on the experimental data set. Some of the experimental researchers, they published a paper in a MOA for functionalized MOA, did the crystallographic analysis, like a single crystal analysis, published it along with his or her paper. That data, you take it and use it in your simulation. So for that reason, that is the collection of structure from the crystallographic file. Then collection of structure from the protein data, that is particularly applicable for the biomolecules, like the protein structures. Nucleic acid, etc. Some of the peptide structures are also available. Okay. So the idea of doing this thing is to get the partial charge. In some of the papers, in the MD papers, so you have read one sentence with respect to the computational methodology that charges are scaled 50%, right? Charges are scaled 80%, 0.8%, right? Okay. So what is that? Let's say LiTFSI. Let's say I take one example. So that's okay. That's the ionic liquid. So let's say this is my Li, and so this is one kind of ionic liquid. Now, okay, ideally, this entire anion should have -1 charge, an entire cation should have positive one charge. You do that, you do the simulation, and when you analyze the trajectory or analyze the transport properties, what you can see that your lithium is moving abruptly. Probably lithium is not moving with the anion. Lithium is going somewhere else, your anion is stuck in somewhere else. At that time, what we have to do? We have to reduce this charge. Let's say we do the 80% scaling. So then it will be 0.8. So there it will be 1.2. Right? No, it is negative 0.8. So when we are reducing the charges, every charge on a particular atom will be scaled. But for that, we need to know what is their original charges on each and every atom. That is called partial charges. So there are various ways like CH, then this AM1 BCC calculation, then the Mulliken charges, etc. And there are particular software packages or the lines of codes are available to extract them from this QC and MN calculation. For this crystallographic and there the partial charges are already mentioned in their particular files. If not, then for the PDB file it is already mentioned, but for this crystallographic structure, if it is not mentioned, then you can do a single point calculation. What is single point calculation? Yes, energy calculation without optimizing the particular molecule. Why? Because you are already taking the optimized structure from the crystallographic file, .scr file. You need to only know the partial charge on each and every atom. That you can do it. And then generally this is a very famous open source package, PackMold, which is used to create the simulation box. Okay, so I just will show some of the PackMold generated systems. You can see that this kind of systems with simple algorithm, 4-5 line algorithm, these kind of systems can be initial geometries can be created. In the next half, when we will go through this GLOMAX simulation tutorial, then we will see what is the particular script. Although these scripts are available. Okay. I'll take 15 minutes more, then I will take a break. So next is the force calculation. Because what is the basis of the MD? Basis of the MD is Newton's second law of motion. It says that the force is acting on each and every particle. So that is the most time consuming part. And how the force and energy are related with this relation. Force and energy are basically related with the dou ux, dou r. That means negative spatial derivative of potential energy. That is the definition of force. Now, if I have a n number of particle system, and if I take the pairwise calculation, because r is the distance, and how do we calculate the distance between two particles, right? Between two particles. So if I have the n number of n particle, then I have to evaluate the distance is n into n minus 1 by 2, because I should not overcount. It is not a permutation, it is between the combination. And then I have to evaluate the forces. Okay. So now this potential energy, it has several forms, right? Nowadays people are using this LJ potential. but it has started with the hard sphere potential. So whenever people started to develop a theory, they generally go for the ideal part first, because that is the easiest way to establish the concept. Then, okay, then slowly they go for the real part. Is this part clear? I mean, this is known to everyone. Otherwise, I will explain. Explain. Okay. So first one is the hard sphere. Okay, hard sphere potential. So it says that hard sphere, that means the, let's say, billiard ball. That means whenever two particles will be in contact, there will be some interaction. That means there will be some energy. And whenever the contact is lost, the energy will be zero. And as these are hard sphere, the particles energy, whenever they are in contact, the energy will be repulsive, right? So it says that if the center of atoms of two particles are here, then whenever they are in contact, their energy is infinite. That means repulsive energy is going towards the positive direction. So attractive energy will go to the negative direction, right? And whenever this contact is lost, the energy becomes zero. Next is, now this is the ideal case, but our situation is not the ideal case. We are dealing with a real case. So next, it is the square wave potential. So, okay, what it says that it gives, it adds one attractive term. What is this? This attractive term is defined with the negative epsilon, which is basically the square wave, like this way. Like this way. So this is my negative epsilon, right? And after that, after a certain distance, it will become zero. This is also an approximation because suddenly the interaction cannot be a wave, and after that it cannot be zero. It is not like that, right? So the next approximation is the Sutherland potential, where it is given as this attractive part is changing with respect to the r raised to the power 6. That means this part remains same, but the attractive part, it will be smoothly truncating towards the x-axis. Now the most practical one is the Lennard-Jones. Now you can see that I'll just explain this. Okay, Lennard-Jones. Let's say, okay, we start with the hard sphere. Whenever we have two billiard balls in touch, they are in the repulsive. Now, what this potential says, okay, whenever they are slightly away, there will be some attraction. Slightly away. But is it so? No. Let's just consider the OH bond of water. So the OH bond, the bond distance is 0.95 angstrom. So let's say oxygen and hydrogen they are connected with each other without any distance. So obviously they will repel, right? So that's why the repulsion energy. But if the oxygen and hydrogen are, let's say, slightly away, will they attract? 0.05 angstrom, will they attract? No. Why? Because still it hasn't reached the equilibrium bond length. For that reason, the Lennard-Jones, you can see that this is not a straight line. This repulsion is not a straight vertical line, unlike the Sutherland and hard sphere. It is slightly tilted because until unless this distance until unless this distance becomes the equilibrium bond length, it cannot be stabilized. So whenever you are working with the Lennard-Jones potential, you see that wherever the diagram is, it is not like straight line. Straight vertical line. It is slightly tilted because for our real case, for our real atomistic scale, the attraction will only start whenever it is attaining a equilibrium bond length. That's why this is tilted. After that, when it is 0.95 angstrom, then the attraction is full. So here, and after that, let's say if it is increasing the distance greater than 0.95 angstrom, the attraction will again reduce. And after some time, it will be very close to the x-axis. So this is the fundamental of the LJ potential. Right? Okay, so now we will go to the integration algorithm. I think we can take a 10-minute break. Right? ये अभी आया नहीं क्या? Yes. So let's go outside and have tea.